so good morning all of you. I think I have got it confirmed from one of you that I am audible and the screen is visible. So I am just starting with lecture 10. So for a brief time we can discuss, let's say for a few minutes we can discuss what we did last time. So we were basically studying the A law and the mu law, and I gave you the expressions for each of the laws, and we saw that this is a technique which compresses the dynamic range of the input. Okay, and because of this compression, the problem where our SQNR, the signal to quantization noise ratio, which was appearing to be a function of the signal power, is no longer dependent on the signal power that much. Okay, it means we have not yet studied these laws into depth, but at the moment this suffices for us to know that these laws somehow makes my SQNR independent of the input signal power. Now what is the benefit? That if at all the person is speaking softly, so whatever SQNR he gets, the same SQNR a person who speaks loudly gets. Okay, so it's not that if you speak softly then your SQNR is bad, and if you speak loudly your SQNR is better. Okay, because we want to make a system which can be used by all and can be deployed easily throughout the city. It means, let us say, thousands and thousands of people can use it without being compromised by the voice quality of each of them. Okay. So I think we did that, and then we did the final thing of PCM, that is the encoding thing. And I just told you that this is what is code and this is the code word. And since from your early days you have been doing the assignment of, let us say, binary numbers to some values, let us say binary code we have been studying. Let us say if you have 8 points or if you have 8 things and you need to represent them through binary code words, then you will use 3 bits, and you start from 000 and then you can go up to 111. Okay, so this you know, so I just left it out thinking that we can do it easily, and this is a very, very small thing. Okay, so we'll start today with few of the things which were pending last time, few corrections, and then we will move ahead. At the moment, I would announce that we are somewhat lacking in as compared to section B. I think they have covered DPCM and now they are on signal space analysis. So I will try to be on time, but it may happen that we need to do some last minute arrangements. Okay, we would also try to at least touch signal space representation. Okay, so whatever we are doing in the class, you can just sit back and listen to it, and obviously you know it that you need to go back and study it yourself so that things solidify in your mind. So first of all, one correction I will start with. Correction was that I said inverse laws I could not find. Inverse laws I could not find in SCLAR. Okay, so I told this class book which we are referring. So in the last lecture I told that you can find the inverse laws in SCLAR, but it is not the case. You can find them. You can find it in the company documents. Those who design in the company documents. Those who design ADC /tech. Okay, the analog digital converters, digital to analog converters, the companies who make ICs which do this operation. So in their documents you can find this. So I have got them. So I am just writing the inverse laws, and they are very, very easily, they can be easily derived from these laws directly. Okay, suppose you have a y, so you can easily solve for x in both the cases. Okay, so very, very easy expressions. So I am not putting that much time there. You can easily verify it. If at all you are not able to do it, if any one of you is not able to do it, and you are still interested to know how it happens, so you can just email me, and then we can have a separate discussion. And if there are more number of people who cannot do it, then we can discuss it in class. Okay. So for the mu law, the expression is that f inverse y, if at all you are given the compressed value y, So how do you obtain the x? That is given by serenum of y into 1 upon mu, 1 plus mu to the power of minus 1. Okay, and here y will lie from minus 1 to 1. That is quite obvious because I think you can see that here while we were defining the mu law, so we said that y by y max belongs to minus 1 to 1. Okay, so we have already said this. So this is the expression for the mu law, and for the A law, f inverse y is given by y. So because it was defined for two cases, so we need to write it for two cases. Okay, then let me write it below so that there is no space condition. This is given by sine sigma y by is equal to pi 1 plus ln a divided by a, and this is for 1 upon 1 plus. I personally checked it from the laws directly. You can derive these inverse expressions. Okay, so there is no problem in that. But if still there is a problem, you can contact me. I will derive it. So this is valid for 1 upon 1 plus ln a less than into. Okay. So these were the two inverse laws. So the correction has been made. One more correction. That is, I might have told that sine function of x might converge to 1 by 2 at 0, but this is not the case. This is defined like this. So one correction is 1, 0, minus 1. Okay. So for x strictly greater than 0, for x equal to 0, and for x strictly less than 0. Okay, so there is obviously a discontinuity at 0. So sometimes, or most of the times, it is drawn like this with two things here, straight line. This is minus 1, this is 1. Okay, this is x, this is sine of x. So I think I remember that I told in the last lecture that this function might converge to 1 by 2 at 0. This should not be the case because this is a sine function. For x equal to 0, it should be 0 without any ambiguity of sign or without any multiplicative factor. So with this, I think we have done what was pending from the last lecture. One more thing, that if at all you are still not clear that how encoding is done, so I am giving you the exact page number, or you can say a reference that you can see table. This is simple. It's like assigning a binary code word to elements of any set. Okay. So on. See, this page 204 of Haken is, let me write down the edition also. So I have the 4th edition, okay? Communication Systems 4th edition. So maybe if you have the 5th edition, so there might be a misalignment of this page number. Maybe it is given on page 202 or 205 or 2010, or sorry, 210. So it depends. You just have to see this encoding procedure. So you can easily recognize if you see the table on any page. Right now it is in chapter 3 of the 4th edition. Okay. So with this we have done what was pending in the last, or what is the carry forward from the last lecture. So now it is important to study. So PCM is done. Okay. So PCM is done, but the engineer's question comes. Okay. I think this is what I have been calling from day one. Because engineers are those people who will try to run the system or who will try to design the system. Let us say if I am a theorist, I have developed the theory, so you are an engineer suppose, so you will come and then ask, okay, then I have to use the theory. So practically I have this much of strength. So immediately you will pop up the question that what is the bandwidth consumption of any scheme which the theorist is proposing. So I have proposed PCM. So I need to know what is the bandwidth requirement of PCM as compared to the signal which we need to transmit. So there was an analog signal. Okay, an analog signal when enters a PCM encoder. Okay, so this is called as a PCM encoder. So it involves all the operations, that is sampling, quantization, finally encoding into a code word. So I will get a sequence of digits, you can say. If at all it is a binary code word, so you will get a sequence of zeros, 1 0 1 0 1, okay, 1 0 1 0, whatever, a combination of bits. So let us say this is band limited to B hertz, then what is the bandwidth consumption of the sequence of digits which I will get? So this is the question which every engineer who wants to make the system run is interested in. So we will do that. Okay, so we need to do it. So let us do it. Okay, we will be doing it in some sort of a different manner. Okay, so you will see, since L is equal to 2 raised to power n, or n is equal to log to the base L, where L is the number of quantization levels, where n is the number of bits used to encode, number of bits used to encode. Okay. You must not use the word 6. Should be V number. We know that. And message signal. Now in the bracket I will be writing analog, so that you know that we are studying it from analog to digital conversion. Message signal empty, band limited to B hertz. Okay. It requires a minimum of 2B samples per second. Okay, this comes from the sampling theorem. So in the bracket I am writing sampling theorem. For those who will directly read notes for lecture 10, and if at all they forget that from where does this come, so I am writing it in the bracket. So this is the fact. We know that it requires a minimum of 2B samples per second we need to take. So how many bits will be generated per second? So we have, let us say, n bits we are using for each of the levels, and the number of samples we have 2B samples per second. So there will be 2 NB bits per second that will be generated at the output of this PCM encoder. If at all there is an input which is band limited to B hertz, and we use the Nyquist sampling rate. Okay, we need to use it. Otherwise, error-free recovery is not possible. Theoretically and even practically, people have found this, that this is the case. So 2 NB bits per second, if at all we are using a binary code. Okay, so I am repeatedly saying that you can use any sort of code, but for the purpose of study and mostly we will be using binary code. So there might be a moment where I forget to mention that we are using a binary code. Okay, but assume if at all we are using bits, we are saying bits, it is a binary code. So 2 NB bits per second, or you can say 2 NB pieces of information per second. So this is what is the output. Now, how do you study? Let us say if you have 2 NB bits per second at the output of the PCM encoders. They are bits. I still need to transmit them. So I need a small analog waveform which I can basically put up to an antenna which will radiate it. Okay. So it depends. I can transfer my spectrum to a higher band through modulation. That is called the band pass modulation. That is a separate story. But anyways, whatever I need to put into the transmitter must be in analog form. So this is a sequence of bits. So I need some sort of a pulse communication where I can convert this bit to pulses. So if at all I need to find the bandwidth consumption of PCM, I need to know what sort of a pulse I am using. So it means that it is impossible to comment anything about the bandwidth consumption of PCM unless I know what pulse I am using to transmit these bits. So that means that we are now stuck. But this is indeed not the case. Here we will use the dimensionality theorem. I have not yet introduced this theorem. I will be just stating it now because we do not need to study it in depth right now. Okay. This theorem basically will help us find the bandwidth or lower bound, that minimum this much amount of bandwidth a PCM system will take, whatsoever pulse you will use. So that's why we need to study such result. Okay, so this gives us a lower bound, that this much minimum you need. So I am stating the dimensionality theorem. So let us say, so let phi jt be the set of orthogonal waveforms. Okay, orthogonal waveforms of duration. See, this theorem is very interesting and this will help you in the long run. Reason being that such questions are generally asked in companies interviews where the company is focused on signal processing or it makes chips, let us say Qualcomm and Analog Devices and several other companies, those who are engaged with the design of signal processing systems or communication systems of duration T and bandwidth W. Okay. Then this is an important result. Then the number of different waveforms. So I am writing WF as the waveforms in the set phi jt is upper bounded by 2dw. Okay, so this is of duration T, bandwidth W, when dw is large. So the interested reader or a more alert reader or a more alert attendee would say that you are saying that there is a pulse or there is a signal phi jt which has a duration T and a bandwidth W. So we have already studied this earlier, that a signal which is time limited cannot be band limited, and a signal is a band limited signal cannot be time limited. So how are you saying that such a signal exists, that phi jt which is of duration T and bandwidth W? So here the meaning of bandwidth W star I would write is, in some sense, star means, let us say some percentage, maybe more than 95, more than 97, 98, lies in a band of width W. Okay, that is the meaning of signal. So this bandwidth W is not the exact bandwidth, the absolute bandwidth. This is a bandwidth in which you can say that most of the energy is lying. The signal, the spectrum will definitely be exceeding from that, because if the signal is time limited, it cannot be band. Okay. So it says that, let us say there is a signal which is of duration T. So ये हम क्यों study कर रहे हैं? Because if we have a bit sequence, 2NP bits per second, so every bit we would be modulating with the help of a pulse. So let us say, so that bit exists only for some time, because we need to stuff 2NP number of bits per second. So you can say that what is the time available for one bit? So that is simply 1 upon 2NP. Okay, this much, for this much seconds a single bit exists. So I need a pulse which takes this much of time, and assume that it needs to take some sort of a bandwidth, because we need to know what is the bandwidth consumption of this PCM system, or we always will be having some sort of a band available to us in which we need to transmit. So we need to use these pulses, or you can say these signals. So how many such signals exist? So then the number of different waveforms in the set is upper bound by 2TW. Okay, इतनी ही different waveforms हो सकती है. ठीक है, अब ये different waveforms हम क्यों study कर रहे हैं और इसका encoding से क्या मतलब है? That we will get to know once we move to module 2. Okay, so that would be easy for you to understand the mapping from this bit sequence to this pulses. Okay, so that will study there. But if at all we know this, then how does it help to find the bandwidth of PCM? So we will see. Okay. So let us say that is n, then the number of different waveforms in the set. So I am writing n. So n is that number. Okay. So you will see that this n, the theorem says that this n is upper bounded by 2TW. Number of different waveforms. Or you can say that W, this is the bandwidth of each of the signal, is greater than equal to n upon n upon 2t. Now what is n? N is the number of different waveforms. So how many, or you can say that n by t is 2np in PCM. How? Because how the number of different bits which you generate per second is 2np, or you have 2np pieces of information per second. So that is n. Now when I am saying per second, so I need to divide it by t. Okay, so n by t is 2np in PCM. Okay. So if I am using this set 5JT to transmit PCM bits, so the width or the bandwidth of each of this will be greater than equal to 2np divided by 2, which is equal to n. So this is an important result which says that although PCM is beneficial, but the problem is that if at all the original signal was of bandwidth b, okay, that the analog signal, if it is of bandwidth b hertz, after PCM encoding, the bandwidth required for transmission will be n into p. Higher the number of bits you use, higher is the bandwidth which you need to transmit. Okay, this should be quite aptly understood. Why? Because there was a single sample. Now this sample, if at all I am using 4 bits, is converted to suppose 0101. So I have 4 pieces of information instead of this 1 piece of information to transmit. So obviously, if I have 4 pieces of information and the time I have is definitely the time which is between 2 samples. Suppose this is t seconds. So I have only t seconds to transmit now 4 bits of information. So I need to reduce the time consumption of each of this bit. Because of this, as you compress the time, the bandwidth expands. Okay. The more the signal is time limited, the more it expands in bandwidth. And similarly, the more the signal is limited in bandwidth, the more of its extension in time. Okay. So you can see this through that principle as well. Otherwise, this dimensionality theorem helps us to get a lower bound. So now, right now, we have not yet specified what our 5JTs would be. So let us write down what do we get. So we need a minimum of, suppose if I call this as B of t, that is a transmission bandwidth. Okay. Minimum of BT hertz which is equal to, let me write NB directly instead of T. That will necessarily confuse it. Minimum of NB hertz to transmit PCM signals. Okay. So bandwidth of PCM signal will be significantly larger than the bandwidth of the corresponding analog signal it represents. Okay, so this is one of the important analysis through which we should conclude PCM. Final thing is when the output SNR is pending, you will do it. But this is an important result which we need to know that at least if I am using some PCM encoding over an analog waveform, it will minimum will take NB bits. Okay. Sorry, this is NB hertz, not bits. So n times का increase हो जाएगा bandwidth. So ये भी एक जिसे कहते हैं no, we can say that this is a drawback, but indeed it is not because you can place several repeater stations in it. So you can expand your wireline network for several kilometers. So this is a benefit which overpowers this bandwidth consumption. Although this puts up a demand on the quality of the wires which are taking this, because you know that any sort of a wire has a bandwidth type of a response. It means that it cannot transmit signals of all frequencies. It also has a response. So this somewhat puts up a constraint on that quality. So that quality can be easily maintained considering people would use this system, they would pay for the services, and the companies can easily survive. Okay, they can pay engineers, they can make products, they can have factories. So this is not of that much of a concern if at all the system is widely used. This result we would definitely come back and discuss, I think, when we will start with modulation, the bandpass modulation, we will definitely, or I think immediately after this, when we will study signal space analysis, then this will be more clear. Okay, but now assume that this 5J is some sort of a pulse, and this is the way we would analyze the lower bound, because we have not yet commented what 5J will be. मिनिमम इतना होगा, इससे ज़्यादा भी हो सकता है और इससे ज़्यादा ही होगा बहुत से केसेस में, बिकॉज वॉट एवर पल्स यू विल डिजाइन in theory it will in practice definitely won't conform to what theory says. Theory will always give you lower bound कि minimum इतना होगा, अब उससे ज़्यादा कितना होगा, आपका डिज़ाइन प्रोसेस कैसा है, आपके सर्किट कैसा है, उस पर डिपेंड करता है. डिपेंड्स ऑन द सर्किट or the way you generate these waveforms, the way you use these waveforms, the quality of your the transmitter and receiver circuit, the noise in them. Okay, so there are several things, but at least you know कि minimum इतना होगा, इससे ऊपर कुछ भी हो सकता है. So now let us go to one last important aspect of PCM, that is the output SNR. Okay. PCM, this is important. This will tell you that what is the effect of number of bits. Let us say we have now seen the effect of encoding on the bandwidth. Now we will see the effect of encoding on the output SNR. See, if you think aloud, so you will see that if you increase the number of bits, the SNR should increase, because if I am increasing the number of bits, I am keeping more representation levels, the noise should decrease. Now we will see that indeed this is the case, but by how much we will answer that. Okay, so this is important. But I think let me write it down. So for non-compending, or where we were not doing any sort of compression and expansion, I derived the formula that S naught, that is S naught by N naught or SQNR was indeed, let me write it SQNR in brackets so that this is clear. So we said that the SQNR is 3L square, the average power of the message signal, divided by the, let us say this is your quantizer whose maximum and minimum range is NP. So this was what was the SQNR for non-compending. For compending, let us say for, you can say mu log compender, for mu log compender. So this I am not deriving, this is not required for us to do. We can simply state it because this is a part of source coding. Okay, so our course is not entirely focused on source coding. It has, let us say, the first module which is primarily concerned with source coding, and that too at a very fundamental level. So a few derivations are not required to be done, so I am not doing it. You can just simply take it, this, and I will give you the reference as well. So this has been taken from VP Latte. Okay, so this is equal to 3L square. So if you do this compending, so this SQNR now changes to ln 1 plus mu whole square. Okay, but the condition for this is, when does this happen is, your mu square must be very, very big as compared to mp square by. So if at all you satisfy this, so generally if you remember, we have taken mu to be 255. So if mu square will be 255 square, that would be a big number. And most of the cases for speech signals, that would be much, much better than this. Okay. So for that case, now you can see the difference. Here it was depending on the signal power, but here it is some sort of a constant, and that is what we want to achieve. Now why I have drawn this symbol is that this is approximately equal to, this cannot be exactly equal to. Here we have used exact equality, but here it is an approximate, you can say that it is an approximate expression for SQNR, and the condition where this approximation works fine or it is acceptable is this. Okay. So if that is the case, so let us now study each of these expression properly. So we can say that S naught by n naught is equal to C times 2 raised to power 2n. Okay. Why? Because L was 2 raised to power n. So if you substitute L here, so this, if we do L square, so it will 2 raised to power 2n, where C is equal to 3m square t divided by mp square for uncompressed case. Uncompressed case. Okay, and it is 3 divided by ln 1 plus mu square for the compressed case. Okay. So in general, we have to see this expression, this C into 2 raised to power 2n. Now you know that the transmission bandwidth B of t, if I define as n of B, so I can write that n is equal to transmission bandwidth Bt divided by the bandwidth of the analog signal. Okay. So S naught by n naught, that is the SQNR, is C into 2 raised to power twice of Bt by B. So what does this imply? So SQNR increases exponentially. So this is a gain, increases exponentially with transmission. Okay, so if you increase Bt, if you have a very large Bt, then your SQNR also increases, and that too, this increases exponential because it is to the power of 2. It is not a linear increase. अगर 2 नहीं होता, simple C Bt by B होता, तो हम कहते हैं that increases linearly or SQNR scales linearly with Bt. But here the SQNR scales exponentially with Bt. Okay, because it is in the power of 2, or there is some exponent over which it is in the exponent to some quantity. A small increase. So this is important to visualize. So a small increase in transmission bandwidth yields a large benefit in terms of SNR, in terms of SQM. Okay, that you can simply see from the expression. Let us see if I write it in terms of dB. So S naught by N naught in dB. This is given by 10 log 10 S naught by N naught, which is equal to 10 log 10 C2 to the power 2n, which is equal to. So I'm just writing everything clearly so that the interested reader is not lost if he or she directly goes through the notes instead of the textbook. Okay. Let us say we write it like alpha plus 6 n dB. So this you will find it a lot of places, this expression, alpha plus 6 n dB, where alpha is 10 log 10 C. Okay, so I just use alpha for this because this is some sort of a constant. This doesn't depend on n. So as you are interested in the case of bandwidth, that what is the requirement in terms of n. So we are now studying the SNR, the output SNR in terms of n. Now 2 log 10 2. Okay, this is 6. If you can say approximately 6. I think log 10 2 must be some 0.03 something. You can check it out. This is simple to see. So this shows that increasing n by 1. Now if I increase the n by 1, suppose if n was 2, now 2 bits I was using to represent each representation level. Now if I do it, let us say now the bits become 3. So I am increasing the bits by 1. That is increasing 1 bit in the code word. 1 bit in the code word. Quadruples we will see how does it quadruples the output SNR. See, we might use SQNR and SNR interchangeably. Do not get confused. Right? We have not yet introduced the additive white Gaussian noise here. So still this is the quantization noise which we are studying, not the AWG. AWG you will study in module 2. From module 2 we will start with the introduction of AWG in the system. Okay. The output SQNR. This is a 6 dB increase. Okay. How? Let us see. That there is a quantity, suppose X, and I say that it has increased and it has become 4 times of X. So in terms of log, let us say if I calculate log 10x, this was log 10x, and this was nothing but 10 log 10x plus 10 log 10 4. Now what is this? This expression is 6.02. Okay. So if this was S in dB, so x in dB, so this is x in dB plus 6 dB. Okay, 6.02, you can say approximately it is 6 to 60. So if at all linearly the quantity becomes 4 times, so in dB 6 dB का बढ़ जाएगा. That is what we are saying. So अगर आप n को जैसे अल्फा प्लस 6n है और आपने n को 1 से बढ़ाया तो अब क्या हो गया अल्फा प्लस 6n प्लस 1 ब्रैकेट में लगा दीजिए. So this will be alpha plus 6n plus 6. Okay. So it means तो अगर ये dB में था, ये ओरिजिनल था, तो 6 dB का इंक्रीज हो गया. But 6 dB का इंक्रीज का मतलब क्या है? क्वांटिटी 4 टाइम्स हो गई. That is what we have seen here. So this shows that increasing n by 1. If you increase 1 bit in your encoding procedure, it is quadrupling the output SQNR. So this is a very you can say a good observation that एक बिट बढ़ाने का बहुत बेनिफिट है SQNR. ठीक है, उसके थोड़े थोड़े प्रॉब्लम्स भी हैं, ऐसा नहीं है, बट वो हम PCM सिस्टम की आप लोग थोड़ा बुक से, इफ एट ऑल यू कैन गो बैक एंड रीड द बुक. Why I again say the interested reader, because there might be a few things which are not covered in the course or which may not be asked in the exam. So it depends on the reader what he or she wants to read after finishing up what is covered in the course and what comes in the exam. Okay, so that's why I say a few things. I say it is for the interested reader. The interested reader can go and read the textbooks in a more deeper sense to get to know this system. Okay, so this shows that in PCM, SNR, SQNR can be controlled by transmission bandwidth. Okay, so let us see an example for it. So this is the first example I am discussing in this course. Okay, so let us say, so this is from the textbook itself. I think I have taken it from most probably BPRT. I don't know. So after this, I have not yet updated the lecture breakup file from the last two lectures, because few things I am doing in connection. It means they are all connected. So I will do it by the end of the day most probably. So MT, let us say there is a message signal and the bandwidth is 4 kilohertz. Okay. So it is transmitted using a binary compend. Binary means there will be binary code words, and compending is used. Some law, maybe A or U. Binary compended PCM with mu equal to 100. Okay, so mu law is used and the value set as 100. So I want to transmit this MT, which is band limited to 4 kilohertz. So the question is, compare L equal to 64 with the case of L equal to 256. Okay. One thing I need to say, that if I am increasing the number of bits by 1, so my bandwidth increases. Let us say PT was NP. So now new bandwidth which will be required will be N plus 1P, or my bandwidth increases by B only. But the SNR increases 4 times. Okay. So via a nominal increase in the bandwidth, I can increase my SQNR by a much bigger value. This you will see. Okay. From the point of view of transmission bandwidth and output SQ. Okay, so we need to do that. So let us do it. So if L is equal to 64, so this implies what is N? N is log 2 L. If at all log 2 64 you find, it will come out to be 8. Oh, sorry, 6. Over 2 raised to power 6 is 64. This comes out to be 6. So transmission bandwidth P of T will be NP, which is equal to 6 into 4, which is 24 kilohertz. Now what will be the output SNR? S naught by N naught, okay, in dB. So this will be alpha plus 6N, which is equal to, let us find alpha. Alpha was 10 log 10 C. So कंपेंडेड PCM यूज किया म्यू के साथ. So म्यू लॉ में हमें पता है कि जो ये C होता है वो 3 by ln 1 plus mu square होता है. So we can just simply put it and find this. So this is ln 101 whole square. This comes out to be some minus 8.51. Okay. Because 10 log 10 is there, so it can easily come out to be a negative thing. And this will be alpha plus 6 into 6. Why? Because n is 6. So this is alpha plus 36 dB. You can now put alpha here, so you will get this S naught by N naught in dB comes out to be 27.49 dB for L equal to 64. Now for L equal to 256, okay, N comes out to be, if I take log to L, it is equal to 8. So Vt is nothing but Np, which is equal to 8 into 4, which is 32 kilohertz. Should be 32 kilohertz. Okay. Now what is S naught by N naught? So the same thing which we have done above. So I am just directly writing it. This comes out to be 39.49 dB. So I am writing out down the observation. So the difference between the two SNRs is SQNRs is 12 dB. Okay, as you can see, if you just subtract both of them, 39.49 minus 27.49, it comes out to be 12 dB, which is a ratio of 16. Okay, so this is a big thing. You have just increased the number of bits by 2, and SQNR is increased 16 times. Okay? Thus, the SNR or the SQNR plus the SQNR for L equal to 256 is 16 times the SQNR for L equal to 64. The former means for L equal to 64, the former requires, let us see the bandwidth. Okay, तो bandwidth increase कितना होगा? अगर 2 बिट से बढ़ाया गया तो bandwidth increase को भी जानना बहुत जरूरी है कि bandwidth कितना बढ़ा. ठीक है, SQNR 16 टाइम्स हो गया, बट bandwidth भी तो बढ़े ना, बिकॉज आपने अभी तक आप 6 बिट यूज कर रहे थे, अब आप 8 बिट यूज कर रहे हैं. तो लेट अस चेक दैट. So the former requires just about 33% more bandwidth compared to later. We will find it out how. जैसे L equal to 64 वाले का जो BT था वो था 24, और L equal to 256 वाले का BT क्या था? That was 32 kilohertz. तो आप परसेंटेज निकाल सकते हैं कितना बड़ा. दैट इज सिंपली 32 minus 24 divided by 24. Because this is with respect to 24, this is 8 upon 24, and if in terms of percentage this is equal to so that clear. In terms of percentage, this is 33.3%. Okay. Why? Because 8 by 24 is 1 by 3, and 1 by 3 is 0.333. Okay, so if you multiply by 100, so this comes out to 33. So initially you are using 24, now you are using 32. So percentage increase 33%. So only 33% increase of the transmission bandwidth gives me a 16 times SQNR. So this is what was the last point of PCA. This was important to study because these are two very important metrics which define the performance of the system, and very important from the engineer's perspective that ठीक है कितना SQNR आएगा और कितना bandwidth कंज्यूम. ठीक है, अब ऐसा नहीं है कि हम bandwidth बढ़ाते जाएं SQNR के लालच में. क्यों? क्योंकि जो आपका सर्किटरी है, जो आपका वायर है, स्पेस सिग्नल को जाना है, उसकी भी अपनी एक लिमिट है. स्विचिंग डिवाइसेस की अपनी लिमिट है कि वो इतने बिट्स इतने सेकंड्स में इतने बिट्स जनरेट कर पाए, उन्हें प्रोसेस कर पाए. ओके, सो थ्योरेटिकली इफ यू कैन do this, then this is what you can get. but you are definitely constrained by practice. It means if you need to make this, no, there will be some wire. Wire has to be made by some element. Maybe it is copper wire, the steel wire, whatever. Although steel wires are not used, but I'm just saying that if you didn't know that from which material you need to make a wire, then there are several possibilities. You need to check every material, how much bandwidth it has, what are all other issues. Let us say you can मिट्टी में आप डाल सकते हैं, उसको नहीं डाल सकते, पानी में वो कैसे सर्वाइव करेगा, तो प्लास्टिक कोटिंग इज देयर. So there are several things. So theory and practice, when both are combined, then the product comes out. Okay. So the last thing is that for those who are not very much confirmed or very much comfortable about 10 log 10 dB anything, so they can just read a section that is comments. This is a self-read. Comments on logarithmic units. Okay. This is a small, very small section. There you can say a paragraph or a section. You can say given on page 280. P.P. Latti's book. P.P. Latti, and I think the second author is ZD, yeah, and Chinese person ZD. Okay. This edition is international edition. Okay, Indian edition 4th. This is the 4th international edition. I think I have written this in the list of textbooks, but I am just again writing it. List of edition. This is the Indian print. Okay, so Indian edition you can get. I think if you search by this, you can get. So this is for those who are not very comfortable with the logarithmic units. Why do we do 10 log 10? Or basically, if at all your signal has a very large dynamic range, if the minimum value it can take is, let us say, 0, and the maximum it can take is 2 lakh. So the dynamic range is quite large. You cannot represent it quite well in a graph. So you need to resort to such logarithmic units to study such systems. Okay. So at the moment, I would say that we are done with PCM. Then we need to go to line. Okay. So we will start with it. Definitely. So if you have anything to say or any comments you want to give, you want to make, you can unmute yourself and say it. Or if you need to talk to me on something, then towards the end of the lecture you can talk. It means once the lecture gets over, I am generally online for 10 minutes. So those who need to talk to me can talk at that time as well. So let us study the line codes. Okay. This is important to know because quite popular, and most of the questions in interviews or at other places are asked from this line code concept because people are quite interested to study this. Okay. So binary. So now binary, ones and zeros. See, this is the output of the PCM encoder. So now we will be studying, because we are very much convinced that PCM encoding helps us implement systems or digital communication systems for larger distances, and it has several benefits from the perspective of system. Okay, implementation से बहुत फायदे हैं. Implementation किया जा सकता है आसानी से इस तरीके के सिस्टम का. तो इसलिए अब हम बाइनरी वंस और जीरोस के ऊपर स्टडी कर सकते हैं कि उनको कैसे ट्रांसफर किया जाए, उनको कैसे पल्सेस में कन्वर्ट किया जाए. जो हमने 5JT पढ़ा ऊपर, वो तो अब हमारा पीसीएम का थ्योरी खत्म हो गया. अब हमें इसको स्टडी करना है, और यही हमारा मॉड्यूल 2 भी है. इट इज अ रिप्रेजेंटेशन ऑफ डिजिटल सिग्नल्स. कैसे 1 और 0 को आप कन्वर्ट कर सकते हैं, यूज कर सकते हैं. एक और बेनिफिट है इस 1s and 0s को कन्वर्ट करने का. देखो, इफ योर वॉइस इज आल्सो 1s and 0s, if your computer file is also 1s and 0s, if your video is also 1s and 0s, so what is the benefit that all of them can be transmitted with each other without constraining on the quality, because now full signal is in terms of 1s and 0s. तो ऐसा नहीं है कि किसी एक टाइप के सिग्नल के लिए हमें अलग प्रोसेसिंग करना पड़ेगा. आज आपका मोबाइल है, it does everything. It can transmit a video, it can have a video call, it can have an audio call, it can have several other things. It can send emails, it can receive emails, SMS, because now the data, now everything is data. मतलब 1 and 0 के फॉर्म में आ गया, एक आपका रिप्रेजेंटेशन हो गया है हर पॉसिबल एनालॉग सोर्स. So that's why this binary ones and zeros or representation of everything in terms of ones and zeros is quite popular, and because of transistor being a very good switching device, transistors can give you logic 1 and logic 0 both. So invention of transistor basically made binary things quite useful and possible in communication. So ट्रांजिस्टर से आप लॉजिक बना सकते हैं 1 और 0. ये तो ठीक है, पेपर पे तो 1 and 0 1 0 लिख रहे हैं, बट ये जनरेट कैसे होंगे, ये यूज कैसे होंगे, ये भी एक बहुत बड़ा सवाल है. जब तक यूज नहीं होंगे तब तक इनकी स्टडी आगे नहीं बढ़ेगी. स्टडी तभी बढ़ती है आगे जब नीड होती है. सो लेट अस से इट इज पॉसिबल टू हैव ones and zeros, then the study on ones and zeros continue for the purpose of digital communication. Okay. So right now we are more linked with PCM, so I will write that binary ones and zeros in PCM may be represented slash converted, you can say, into electrical pulses, which will be called as waveforms as well, for the purpose of transmission over the channel. Okay. This process is called, we have not yet studied this process, so that's why I am introducing this. So this process is called line coding or transmission coding. Okay. So let us study the major categories. You can say that this is lines. So you can write major categories of LC. So one is RZ, which is return to 0, and another one is NRZ, which is non-return to 0. So what is the meaning of this? So RZ में क्या होगा? Waveform returns to a 0 volt level for a portion of the bit interval. Usually this is 1/2. We will see. Okay. Now what is happening is that suppose if you are using this to represent 1 in some time duration, let us say this is t. So if it is RZ, so for half of the time this will 1 and this will return to this level for another half. Okay. If this is suppose this is your time which is assigned to 1 bit. So in this duration, this waveform returns to 0. That is what is written. So waveform returns to a 0 volt level for a portion of the bit interval. So this is a bit interval, suppose t. So for this, if at all, so this will return to 0 for a portion, and this portion usually is taken to be 1/2. Obviously, this can be like this as well. So like this, it is less than half, or more than half. Okay. But usually it is 1/2. Now further classification. Further classification is according to the rule is according to the rule used to assign voltage levels to represent the binary data. Okay. So one classification was based, let us say, category was RZ and RZ. Now another classification which you can do is according to the rule that is used to assign voltage levels to represent the binary data. Let us see; it will become more clear once we are done with classification. So based on this, one is unipolar. Okay, unipolar means that it has only one level. So 1 is represented as plus A volts and 0 is represented as 0 volts. See, why are we studying this is, see, अगर आपके पास एक सीक्वेंस है 1 1 0 0 1 1 1 और हमें पता है कि एक बिट के पास बिट इंटरवल सपोज TB, so why not we simply use a normal rect function to represent this? Means आपने 1 ले लिया TB के लिए, फिर TB के लिए 1 है, दैट इज ड्यूरेशन के लिए, फिर ये TB के लिए 0 हो जाए, फिर ये TB के लिए 0 हो जाए, फिर ये TB के लिए 1 हो जाए, फिर ये 1 रहे और फिर ये 1, इस तरीके से 1 1 0 0 1 1 1, where this is the bit interval TB. I am writing it to be the bit interval. This is bit interval. So ये सबसे बेसिक टाइप का conversion है from this 1010 to a analog waveform. There might be a channels where we don't need to translate this analog waveform to a much larger band or to a much higher carrier frequency. We can simply transmit this as well. Let us say जैसे kits आप लोग use करेंगे. अभी तो आप लोग, I think virtually you are just seeing that how our TAs are generating signals in kits. If at all the lab would have been on campus, so you would be given kits where you would do it. So for the purpose of those kits, if at all wires are there, you can transmit this directly. This sort of a waveform, okay? And in some situations, this waveform also works fine. Let us say over in telephone communication also. So if this is the case, then the designer is now coming up with different possibilities. कि 1 को 1 ना रखते हुए हम आधे टाइम के लिए 0 करते हैं तो क्या होगा? 0 को 0 ना रखते हुए एक माइनस लेवल से रिप्रेजेंट करें तो क्या होगा? So ये सब जो स्टडी है, this falls in the category of line codes, okay? And they are used at several places. तो वही हम लोग थोड़ा सा स्टडी करेंगे इसको। अदरवाइज अगर कोई दूसरा एप्लीकेशन है तो जरूरी नहीं है कि आप एक रेक्ट फंक्शन यूज करेंगे, यू कैन यूज अ डिफरेंट पल्स शेप एज वेल। आप हमने क्या स्टडी किया है, सिंक पल्स स्टडी किया है। अभी हमने पल्सेस स्टडी नहीं की है वैसे, बट एटलीस्ट वी नो दैट देयर इज सिंक फंक्शन व्हिच कैन यूज टू शेप द सिग्नल, सो दैट इज आल्सो यू कैन से इट्स द पल्स, or you might use something which is a softened version of this. It means instead of using this, you can use like this, something like this. Okay. So this is all the study which we will do after line codes. That is when we will be studying digital communication, or when we will study the ISI avoidance criteria. There we will go through it. So this is also called as on-off keying. This is unipolar, then obviously comes a category of polar. 1 and 0 by equal positive and negative levels. This you can clearly remember by the term uni means only one level, and you are not using uni, you are simply polar. Polar means two levels, okay? 1 and 0 by equal positive and negative levels. Okay. Now there again comes a quantity which is called a bipolar. Assuming that polar is 2, so bipolar is somewhat ternary, or this is called a pseudo-ternary. It is the name which is given to it. Pseudo-ternary. Okay. So what happens in this is that one is represented as alternately positive or negative value. Positive or negative value. Okay, and 0 is represented by 0 level. So you can say that we have 3 levels. Okay. So 0 level is now retained with the polar thing. It is polar में 1 और 0 दो equal, जैसे से plus a minus a, 2 levels. बाइपोलर में प्लस ए माइनस ए प्लस जी तीनों 3 लेवल्स होंगे, बट प्लस ए माइनस ए 1 ही यूज करेगा और वो अल्टरनेटली यूज करेगा. नाउ व्हाई ऑल दीस थिंग्स आर डिजाइन्ड इज बिकॉज दिस विल हेल्प यू detect 1 and 0 very easily at the receiver. So all these schemes are basically have two perspective. One is the bandwidth consumption of each of them, कितना bandwidth consume करेंगे, और आप देखेंगे कि सबका bandwidth अलग अलग होगा. और दूसरा बड़ा एक्सपेक्ट है कि डिटेक्शन परफॉर्मेंस की रिसीवर पे इस फीचर की वजह से, क्योंकि क्या है आपका डेटा ऐसा भी हो सकता है कि फॉर अ वेरी लॉन्ग टाइम अ सीक्वेंस ऑफ जीरोस कम्स, maybe it has 100 zeros and then 1 1 1 comes. So now this might lead to a loss of synchronization. Okay? We have not yet introduced what is synchronization, but for the purpose of study right now we can say that such a long sequence of zeros or long sequence of ones disturbs my receiver if it is not basically designed properly. So we need to avoid this. So that's why these all schemes have been designed keeping one or the other issue in mind, and that is what you can say a hack which is done, that alternatively positive negative values आप दे सकते हैं उनको. इसकी प्रॉपर स्टडी है, ऐसा नहीं है. तो लिमिटेड स्टडी तो हम लोग करेंगे बिकॉज that is what we can do in the limited time which we generally have in our courses. So what is it? That is use of three encoded signal levels to represent two level binary data. Okay. This is also called okay, this is called as alternate mark inversion. So this is what is your AMI. Finally, let me just introduce the Manchester, and then we can close for the day. This is most probably you should go. Let us see Manchester. So one is represented as positive half bit period, pulse followed by a negative half bit period pulse. Okay. And 0 negative half bit period pulse followed by a positive half bit period pulse. This is also called split phase. Split phase input. Okay. So if at all, basically, let us, I think, see this. So this is what the line code is. So unipolar, let us check what we have written. So in the case of unipolar, let us say the signal, the bit sequence is 1, 1. Let me just more. Yeah, that will be better. So this is the binary data 11011001. Let us not see the punch tape. Punch tape is right now not our topic of studies. Let us say the unipolar. So unipolar, we said that 0 will be with the 0 level and 1 will be with level A. So for 1, 1, level A is maintained. The 0 comes, then there is level A, then again 2 zeros. And for polar, we said that equal and opposite levels. So for 1, if it is A, 0 it has to be minus A. So plus A is there, then it is minus A, plus A minus A. Now for unipolar, return to 0. So return to 0 means कि half bit में उसको 0 पे आना चाहिए. Okay. So unipolar में फिर 1 है, A level A रहा, फिर वो half bit period में 0 हो गया. फिर वापस क्योंकि 1 है तो A रहा, फिर 0 हो गया. And then this is what is followed. Then we have bipolar RZ. Okay. Now bipolar says that if at all you have, let us say, if for this one you have used the positive level, then the next one you need to use the negative level. And if it is returned to 0, so obviously this pulse will exist for half bit period and has to return to 0. So पहले वन के लिए आपने प्लस से यूज किया, फिर वो आधे बिट पीरियड में 0 हो गया, फिर माइनस से फिर 0 हो गया, एंड दैट्स दिस थिंग कंटिन्यूस. सो आप आरजेड और साथ में यूनिपोलर को कंबाइन करके सोच सकते हैं. सिमिलरली यू कैन थिंक आरजेड कंबाइंड विद बाइपोलर, and then final is the Manchester NRZ. So Manchester non-return to 0. So let us revise what Manchester was. So for positive half bit period it is 1, and for the other negative, for the other half bit period it is minus 1. Okay. So this is plus, then this goes on, and this is 0. So 0 के लिए क्या था? Let us say this was 0. So in this case for 0 it was negative half bit period pulse for, or you can say level for 0, and then the positive. So this is what you can relate to. So this is the Gauch's book. Okay. So one final comment which I need to write in this is, so the above terminology where we have picked, let us say the question is कि terminology कहाँ यूज होती है, कहाँ से इंस्पायर है, कहाँ से आई है. So the above terminology is consistent with telephone industry. Okay, so this is used in telephone industry. So some different terminology may be used at other places. Some different terminology may be there for other cases. So I think we are done for the day. This is what we wanted to cover today. Okay. So those who want to stay back and talk to me on some issue, they can. Others, they may leave. Next class we will do differential coding and then DPCM. So we will close module 1 at that point. Okay, once we are done with DPCM, then we will move to signal space representation.
Yes, sir.